everybody, welcome back. Today we're going to be doing another tutorial in Jamovi. Specifically today we're going to be covering how to conduct a multiple regression in Jamovi. So I've got a dataset linked in the description below. I highly encourage you to do this along with me, so you can go ahead and download that and open it up in Jamovi, and we will get into it. So by the end of this video, what I want for you is that you're going to be able to know how to conduct a multiple regression in Jamovi, including how to make sure that you have met the assumptions of a multiple regression. And then importantly, I really want to walk you through all of the output that Jamovi gives you after running a multiple regression so that you have a good understanding of what that output means and how you can successfully interpret it once you've got it yourself. The research question that we're going to be working with here is we're wanting to know, do experimental drug dosages and room temperature together predict heart rate during sleep in athletes? So if you watch the simple linear regression tutorial, we're basically building off that initial question of, does a experimental drug dosage predict athletes' heart rates while they're asleep? But now we're adding in an additional predictor of room temperature. So to back up just a little bit, let's talk about what a multiple regression is and the kinds of situations in which you might use a multiple regression. So a multiple regression is a statistical technique that predicts scores on one continuous outcome, that's the dependent variable, from two or more predictors. In plain English, we would say, it lets us see how well several variables together explain or forecast another variable while giving each predictor its own weight. So equation-wise, our regression equation is going to be y equals bx plus a. So y is our outcome, b is our slope, x is our predictor variable, and a is our y-intercept. So this kind of statistical analysis is going to be perfect when you have a continuous outcome variable. You have at least two predictors, and those can be either continuous or they can be nominal or ordinal variables as well. And you also have a theoretical reason to believe that those predictors jointly would matter. So to follow along with me, you'll open up your dataset in Jamovi, and you're going to go to Analysis and then Regression and Linear Regression. You're going to move over our dependent variable of sleeping heart rate into that dependent variable spot. And then you're also going to move over two variables, because we have two predictors in this analysis, into the covariate spot. And the reason you're putting it there is because both of these variables are continuous. If you had a variable that was nominal or ordinal, you would put that in the factors spot. So you're going to move over the dose manipulation of the experimental drug and the room temperature manipulation. Those are our two predictors that we're trying to use to measure our outcome of sleeping heart rate. Now let's pause for a second to talk about some assumptions. Assumptions are a series of standards that you have to meet prior to being able to fully interpret the results of an analysis. We want to make sure that our interpretation is accurate, and for it to be accurate, we need to have met those assumptions. So for a regression, we have several. One, we have the assumption of independence. This assumption states that all of the data points are independent of one another. This is a very important assumption, and also one that you typically handle prior to the analysis process. So if you're an experimenter or a researcher, you're going to be really focused on independence when you are collecting data or designing your experiment. Less so once you get to the analysis phase for the most part. But I will talk about some other assumptions that we will address in the analysis phase. The next one is going to be linearity. So we want to know that the relationship between our variables of the predictor and the outcome is a linear relationship in order for us to run a multiple regression. To test that next assumption of linearity, you're going to go to Analysis and actually click on Exploration and then select Scatterplots. Then you're going to move over our outcome variable of sleeping heart rate to the y-axis, and then one at a time we're going to check the other predictors, and what we're looking for is to make sure that they do indeed have a linear relationship. So I'm going to move over the dose manipulation variable to the x-axis first, and I can see by examining the plot here that we indeed have a linear relationship. And then I'm going to do the same with the room temperature manipulation variable. And again, I can see that there is a linear relationship between the two variables. So I have checked my assumption of linearity and confirmed that it has indeed been met. Alrighty, so now that we have confirmed that we have met the assumption of linearity, we can take a look at some of the other assumptions. So if I go back into that regression tab that we were in earlier, then under the assumption checks, I also want to take a look at something called collinearity. Now that we have two predictors instead of just one in the model, another thing that we need to be mindful of is we don't want to add in predictors in the model that are highly correlated with one another. So this collinearity statistic is going to help us make sure that the variables that we have in the model, so for us that's going to be the room temperature and then also the dosage of the experimental drug, that those two variables are not too highly correlated. To give you an example of where this could be a problem, let's say that you want to include someone's age in a model as a predictor, and then you also include grade level. Well, age and grade level are two variables that are probably going to be really highly correlated, and so you probably don't need both of those in the model. So collinearity will help us know if our two variables are too highly correlated with one another. And when you ask for that information, Jamovi is going to give you something called a variance inflation factor, or VIF statistic. And what we're looking for there is that the value for that VIF statistic is less than 5. So here it looks like we are less than 5 for our VIF statistics for our predictor variables, so we are good. We have met that assumption. Next, you can take a look at normality. So if you click normality test, you're going to get a result for the Shapiro-Wilk test. And what we're looking for there is that the p-value is greater than 0.05. If our p-value for the Shapiro-Wilk test is less than 0.05, then that means that we have violated the assumption of normality because our data are too different, statistically significantly different from the ideal normal data. So normality says that we want for the dependent variable to be normally distributed in the population, and the Shapiro-Wilk test looks at exactly that. So here we are good again. The p-value for our Shapiro-Wilk test is well above 0.05, so we have also met that assumption. One of the next assumptions that we want to check is something called heteroscedasticity. Now, to test this assumption, there are a couple of things that you can do, and I'll make a recommendation. So one, you can look at a plot of the residuals, and what you're looking for there is that the shape of that plot is roughly rectangular. The problem with that is that anytime that we're relying just on a visual inspection of something, there's a lot more room for error, and you might be thinking, I'm not sure, where's the line? Is it rectangular? Is it not? And so what I like to do is in Jamovi, you can go to modules and then you can type in more tests and you can add that module to your Jamovi library. When you do that, you'll have access to even more tests for your assumptions, and that makes life a whole lot easier when it comes to examining heteroscedasticity. So if you do that, when you select for the normality test, Jamovi will also bring up a test for heteroscedasticity, and we can take a look at the p-value for something called the Breusch Pagan test. So same as with our other assumptions, we are looking for a p-value greater than 0.05 to confirm that we have met the assumption. And here we have a p-value that is well above 0.05, so we have indeed met the assumption of heteroscedasticity. If you'd like to also visually inspect the plot, that's fine too. And all you have to do is request a plot of the residuals, and you can check that to see, is it roughly rectangular in shape? We've talked about assumption, linearity, normality, collinearity, and heteroscedasticity. Lots of assumptions with multiple regression, but important to go through all of those here together. So now that we've tested the assumptions, we've made sure that they've been met, we can go ahead and move forward. So go ahead and click on the model fit box, and you should have R and R squared automatically selected. Go ahead and also select adjusted R squared. Then I'll have you scroll down to model coefficients, and you're going to select for the estimate, the confidence interval for the estimate, and the standardized estimate and its confidence interval as well. Now we've got a whole lot of output here, and we can go through it box by box together. First, we'll look at the results for the model fit measures. Here we have the overall model test. So this is going to tell us if our model as a whole, including both predictors, significantly predicts the outcome, in this case, sleeping heart rate in beats per minute. So we have a statistically significant p-value here. What this tells us is that these predictors together in this model significantly predict sleeping heart rate. However, we don't know which predictors are statistically significant, or if they both are, or how much they contribute to the model. That we will find out in the next table. So for this table, all we know is, yes, something about this model significantly predicts our outcome of sleeping heart rate. We're also given a value here called R and R squared. So R tells us a correlation. It's a correlation coefficient, the correlation between the outcome and the predictors. R squared is the effect size for a regression, and by squaring that value you are given something called the coefficient of determination, and we interpret that as variance explained. However, this value can often be a little bit biased upward, so what I always recommend is that you select instead for the adjusted R-squared value, which controls for a little bit of that inflation. So you'll see our value of R-squared is 0.878, and our adjusted R-squared value is just a little bit lower, it's 0.877. And the way that we would interpret that is that we would move the decimal point over 2 places and say that 87.7% of the variance in sleeping heart rate of the athletes can be explained by a combination of the room temperature and the dosage of the experimental drug. So that's that first model fit measure. Now, when we move down to the model coefficients table, we can get more information about what the individual predictors are adding to the model and how to interpret those. So firstly, we have the estimate. Now, this is the value of the predictors in the measure that they were initially measured in. So what does that mean? Let me tell you. So you see we have a value for the dose manipulation of the experimental drug. That value is in beats per minute, so 10.33 beats per minute. For each additional dosage of the drug, the athlete's heart rate increases 10.33 beats per minute. Then here, for room temperature manipulation, we have a value of 5.37. So for each additional degree that is increased, the athlete's heart rate increases 5.37 beats per minute. Now, we also have the standard error for that value. We have the upper and lower limits, and then you'll see we've got some p-values here. So whereas the first table told us if the overall model was statistically significant, this table breaks it down by predictor and tells us which predictors are statistically significant. And in this situation, both of our predictors are statistically significant. What I want to point you to now is the standardized estimates. So we had the unstandardized estimates before, where we talked about 1 unit increase in the dosage of the drug or 1 degree increase in the room manipulation. However, when we take those values and put them in standard deviation form, it makes it a lot easier for us to compare them and see which is contributing greater to the model. So what is a comparison of an increase of a degree versus an increase of dosage of a drug? How do we compare those? They're not the same thing. So when we make them standardized, then we can better compare them. So you'll see that for the dose manipulation of the experimental drug, that standardized estimate is 0.824 standard deviation units, whereas for the room temperature, it's 0.377 standard deviation units. So that tells us that there is a greater increase in heart rate for the 1 unit increase of the dose manipulation drug compared to the room temperature. That value is more than double in terms of standard deviation units compared to the room temperature manipulation. So that's why the standardized estimates can be really, really helpful in understanding which of these predictors is contributing more to the model. And then of course, we also have the confidence interval. Now, if you needed to construct a regression equation, you could also use this table here. Remember, our regression equation is y equals bx plus a. So y is going to be our outcome variable, the thing that we're trying to predict. So that would be the athlete's sleeping heart rate. Then b is our slope, and we have 2 because we have 2 predictors. So we'll have the slope of predictor number 1. That's going to be the slope for the dose manipulation of the experimental drug. That is the same value as that estimate. So that would be 10.33. And we multiply that by x, which is the predictor, the number of dosages of that drug. And then we would add our next predictor in. So our next predictor is room temperature manipulation. So the slope for that is 5.37, which we would multiply by whatever the additional manipulation is for that room temperature. And then our y-intercept is that last piece, that a. So here, that's going to be the intercept estimate, and it is 50.17. What this means, interpretation-wise, is that if there is no dose of the manipulation drug, If there is no room temperature manipulation, if both of those values are 0, the person's heart rate would be about 50.17 beats per minute. So I'll have that regression equation shown here so you can take a look at it, but that is how you could pull the information from the model coefficients table in order to write and then interpret your regression equation. So we've walked through what a multiple regression is, how you can run that regression in Jamovi, including testing the assumptions, and then how to interpret the output. Multiple regression is really where things start to get a bit more complex and you have lots of options and things that you can do. So if you do have questions or want me to elaborate on anything, I'm happy to do that. Let me know in the comments, or you can ask me through my website, ajoytoteach.com. Thanks so much. Bye.